Hello, calculus students. Dr. Shragi here, and I hope that everything is going well for you at your house and that we're able to all think about this as an interesting story before just too much longer. All right, well, let's move forward. I think this is section 4.5 in your book. It's about the section is labeled derivatives in the shape of a graph. What this really is about, it's two important terms in this course, the first derivative test and the second derivative test. But what these are going to be about is figuring out what the graph of a function looks like based on things like its derivatives. And, in the era of Desmos and similar such, graphing utilities, it's hard to remember that used to be a really hard thing. It used to be really hard to just know what a graph of something was going to look like. Nowadays, you just key it into the Desmos app and you've got the graph perfectly right away. But that isn't always the case. It wasn't always the case, and it might not always be the case if you don't have access to tools or whatever. So today we're going to be learning how to use the second derivative test and the first derivative test in order to understand what a graph is going to look like. Now, make sure you get a copy of the handout that I have for you. It's called Derivatives in the Shape of a Graph handout. And I'm just bringing it up on my tablet today. And what we're going to be doing here is we're going to start by talking about the first derivative test, which I think is going to be the one you're going to be happier with overall. The first derivative test is, first off, you have to notice something about about a function and its derivative and the sign of the derivative. I want you to look at this function that I have right here, and I want you to notice that there is part of the function here where the derivative would be positive. See how the slopes of tangent lines there are positive? And there's a place, there's an interval here where if I drew any tangent lines, their slope is negative, so the derivative would be negative. And then look, there's another interval here where if I made the slope of the tangent line there, it would be positive again. And there is another region here where the slope would be negative. In fact, we could talk about like a couple of different intervals here. Here's one interval. It's kind of hard to draw this on the side. Here's another interval. And here's the final interval, where like here the derivative was positive. We would say that the function was increasing. I'll just abbreviate that INC. We would talk about how in this interval here the function's derivative was negative, and we would say the function is decreasing. I'll just abbreviate that. And then we have another interval from here to here where the function's derivative is increasing, is positive, so the function is increasing. And we have another interval here where the function's derivative is negative. And we would say that the function here is decreasing as we go. So the derivative is either positive or negative in each of these regions, in each of these intervals, if you will. And that is telling us about whether the function is increasing or decreasing. All right. Well, depending on how well you visualize what we're talking about with derivatives, that's not exactly breaking news. On the other hand, that turns out to be kind of important because of these places where, they're the endpoints of these intervals here. You'll probably notice that these endpoints here are critical points. Don't forget that term, critical points. Critical points, remember, are the places where either the derivative is 0 or the derivative is undefined. Well, in fact, these are all places where the derivative is 0. And look what happens at each of these places here. Before that critical point, the sign of the derivative was positive, and after that critical point, the sign of the derivative was negative. In other words, before that the function was increasing, and now the function is decreasing. That makes this one a local max. Similarly, let's look at this one right here. Before it, the derivative was negative. After it, the derivative was positive. Before it, the function was decreasing. Now the function is increasing. That makes this place here a local min. And if we talk about this one right here, before it, the function was increasing. Before it, the function was after it, the function was decreasing. That makes this one a local max. And this is, wow, what a mess. But we'll do some examples with that here. But this is all just a fancy way to say the first derivative test. For the first derivative test, we're going to have a strategy that involves doing what I just did there, kind of in sketchy diagram here. I'm going to find my critical points and use them to break it up this functions up into these little intervals. Here's an interval from negative infinity to here. Here's an interval from here to here. Here's an interval from here to here. And here's an interval from here to positive infinity. And then I'm going to figure out what the sign of the derivative is in each of those intervals. And from that I can figure out whether those critical points were maxima or minima. Now there is one little caveat here. Notice that we found a maximum. Let me sketch something here for you. Let me sketch something that looks like this. Here's my graph, and it's going to look like this. Okay. Clearly I have a critical point here because the derivative is equal to 0. I clearly have a critical point here because the derivative is equal to 0. And let's say I have a critical point here because the derivative is equal to 0. Okay, that means I have some intervals here. I have the interval from negative infinity to this place. Let's just call that A for now. We have another interval from A to B. We have another interval from B to C. And we have another interval from C to positive infinity. Alright, so we could check the sign of the derivative in each of these intervals. Well, we'd have an equation that does this, but I want to just do it now by thinking through. Well, clearly this is increasing. This domain, the interval from A to B is clearly decreasing. Not the function is decreasing, not the derivative. The function is clearly increasing from B to C, and the function is clearly increasing from C to positive infinity. So in this domain it's increasing, in this domain it's decreasing, in this domain it's increasing, and in this domain it's increasing again. Alright, so this was what our first derivative rule said. At this critical point, before it was increasing, after it's decreasing, by rule, hold on just a second, I got logged out of my tablet. Alright, this is rule I in that first derivative test on the first page of your handout, is that that means that this is a local max. This point right here, B, before it was decreasing, after it was increasing. So before that point it was decreasing, after it was increasing, by rule I guess that would be a 2, I don't, anyway, this is a local minimum. Let's look at point C here. It's also a critical point, but before it was increasing, and after it was increasing, by rule 3, did they say inconclusive? It is neither. It's not a maximum or a minimum. We'll learn the word inflection point in a little bit. Typically those will be inflection points. Alright. But I kind of again walked us through the strategy that's on your handout too. This problem solving strategy, which I actually just cut and paste obviously from your book. But basically what we're going to do is we're going to identify the critical points and divide up the function into intervals based on those, with those critical points being the endpoints of it. And then we're going to determine the sign of the derivative in each of those intervals. And from that we'll figure out whether each of those critical points is a local maximum, a local minimum, or neither. Alright, probably the best way to do this is just to go ahead and jump into one of the examples in the book. And what we're going to be using here is example 417 from your book. It says use the, let me write that down here, 417. So in example 417 from your book, it says use the first derivative test to find the location of all local extrema for this function here, and then use a graphing utility to confirm your results. Okay, so our original function will be f of x is equal to x cubed minus 3x squared minus 9x minus 1. Alright, now, according to the strategy that we were given in this book, the first thing to do is to find the critical points of this function. Remember, critical points are the places where the derivative is 0 or undefined. Well, this is just a simple polynomial. It's not going to have any craziness of divided by 0 or anything like that, the way like a rational function would. So far so good. We do, though, still need to find the critical points, the places where the derivative of this function is equal to 0. So let's find those. Let's see. 3x squared minus 6x minus 9 is the derivative, and we're going to set that equal to 0 and find the values of x that makes that work. Now, you could use the quadratic formula, you could use factoring. I actually factored a 3 out of this whole thing first, divided both sides by 3 to make the math a little easier when I did this. And then even I can factor that, and I'm terrible at factoring. Let's see, that's going to be a 3, and that's going to be a 1, and that's going to be a positive, and that's going to be a minus. All right, so this is my favorite rule. What is it? The zero product rule. Two numbers multiplied together making 0 means either this one's 0 or this one's 0. So either x equals 3, so that this term equals 0, or x equals -1, so that that term equals 0. All right, my favorite trick. All right, so we have found the two zeros or roots of the derivative. These are the two critical points. These are the places where our function has a derivative that's equal to 0. All right, now with that information, we can now divide up. I don't know yet what my function looks like, but I know that it has some subintervals here from -infinity to -1, another subinterval from -1 to 3, and another interval from 3 to positive infinity. It's doing something up until a critical point that's here at x equals -1. It's doing something else until it hits the critical point x equals 3, and then it's doing something else from 3 to positive infinity. All right. So all we got to do now is figure out what is the sign. We need to know, is it increasing and then decreasing and then increasing, or what? We need to know what the sign is of the derivative in each of these intervals. All we got to do is just try any old place that we want in each of these intervals. So we know our derivative is this. So let's just plug in a place. Now in the handout there I used, all right, any place in this interval will be the same. Actually, that's a theorem that is in the book, but they don't bother proving, that shows that throughout this interval here, from -infinity to -1, the sign of the derivative won't change. So I can pick any place I want. As it happened, I picked x equals -2, and I'm just going to find out what the sign of the derivative is there. So f prime of -2 equals, and then I did it in the handout, I just plugged in 3 times -2 squared times, minus 6 times -2 minus 9, and I got, yeah, it was 15, which is greater than 0. So the function is increasing in this interval. I don't know yet what it looks like exactly, but it increases. Now let's do this interval from -1 to 3. All right, again, whatever the sign is of the derivative in this interval, it's the same sign throughout. So I can pick any old place I want in there. Just to make the math easy, I chose 0 when I did the handout. I need to know what the derivative at 0 is, because it's between -1 and 3. And I plugged in 3 times 0 squared minus 6 times 0 minus 9. It's going to be equal to -9, which is a negative number. So the function is decreasing in this interval from -1 to 3. And then we got to check this other interval from 3 to positive infinity. Again, we don't know yet what the function is exactly going to look like here, but we know that whatever the sign of the derivative is in this interval, it's going to stay that way. So we can pick any point, and as it happens, I decided in my handout to use 10. So we want to find the derivative at 10. And so I plugged that in over here. 3 times 10 squared minus 6 times 10 minus 9 happens to be equal to 231, which is clearly greater than 0. So the function is increasing. All right. So from -infinity to -1, the function was increasing. From -1 to 3, the function was decreasing. And from 3 to positive infinity, the function was increasing. In other words, -1 has to be a local max. Positive 3 has to be a local minimum. And then the function goes off like this. And see, we have a critical point here where the slope was 0, and a critical point here. Now, we don't yet know exactly what, we can plug into the function and then start making graphs and seeing what this thing looks like. But you can see that we have the general idea. We know that this is a local maximum. We know this is a local minimum. And in fact, the book asks us to go ahead and make a graph of this. And I did that on that handout right there in Desmos. And I would say it checks out. It looks to me like we got the right graph. Whew! That's pretty cool. Notice that this illustrated that rule I, where it found a local max. This is part of that first derivative test. And this one illustrated that rule II, which meant that it was a local minimum. Okay, but we didn't actually come across that third part where it was neither. And probably the path of least resistance to do that is to just do an example where it's in where we come up with that example with an inflection point like that. All right. Before I do that, I should tell you a joke. Somebody emailed me a good joke the other day. A high school student was about to graduate and was asked to give the valedictorian address. And he got up to the microphone and he said, "I'd like to talk today about my mother. She's the most amazing woman in the world. I wouldn't be here without her. I wouldn't be having these successes without her." And then he looked down at his notes and he paused for a long time and he said, I'm sorry, my mother's handwriting is hard to read." That's a great joke. I love that joke. All right, anyway, let's move on and do an example that has an inflection point, which is example 418 in your book. All right, now, again, the instructions are basically the same. It says, use the first derivative test to find the location of the local extrema for this function, f of x equals 5x to the 1/3 power minus x to the 5/3 power. All right. Ugly. Okay. And then it says use a graphic utility to figure out if your answers are correct. Okay. First thing we're going to have to do is find the critical points. And to find the critical points, which are the places where the derivative is either 0 or undefined, we're going to need to know the derivative. I actually did the derivative in fairly painful detail for you in the handout there, and it's a mess. So let me just write the answer down for what that equation ends up looking like. It's x to the 4/3 all over 3x to the 2/3. Now you can certainly ask me if you have questions about how we got it. You can work through that yourself. It's just a little bit of a mess. It took quite a few steps to get to that derivative. All right. Remember, critical points happen where the derivative is either 0 or undefined. Let's find the undefined ones first. Undefined ones generally happen where the denominator goes to 0 and the whole thing just blows up. So that's going to happen in places where this denominator was equal to 0. We could divide that 3 out from both sides. What number to it says the 2/3 power is 0? That's only going to happen at x equals 0. So this is one of our critical points. There's a critical point in our function at x equals 0. How about the situations where the derivative of the function is 0? That's generally going to happen where the numerator of the function is equal to 0. So we're going to have the numerator of the function equal to 0. Let's divide through by the 5. And let's subtract that over to the other side. 1 equals x to the 4/3 power. That works out to x equals plus or minus 1. Now I put a little caveat in your notes there. It's actually some fairly fancy algebra 2 stuff to figure out why it would both be both plus and minus -1. I invite you to figure that out. But I would not, like on an upcoming test or whatever, actually give you any problems where like, oh my gosh, you got to drag up fancy exponential rules and so on. All right. But the point here is we have found 3 critical points in our function now. There's a critical point at 0, there's a critical point at -1, and there's a critical point at +1. With that information now, we can start drawing up what we think our function is going to look like and start doing some tests. Let me clear some of this stuff out. All right. I'm going to make myself a set of axes here. All right, we know that there's a critical point at x equals -1. We know there's a critical point at x equals 0. And we know that there is a critical point at x equals 1. So we have a couple of domains here. We have an interval is the right word here. An interval from -infinity to -1. An interval from -1 to 0. An interval from 0 to 1. And an interval from 1 to infinity. And we can go ahead and pick any old place we want inside of each of these intervals and find out at least what the sign of the derivative is. That's all we really need. All we need is a sign of the derivative so we know whether the function is increasing or decreasing in that interval. And then we'll be able to figure out, using the first derivative test, if each of these critical points is a maximum, a minimum, or an inflection point or something like that. All right. Now that is what I did with those next 4 bulleted points on the graph here. Like, for example, I chose to find the derivative of f of x at -2, and you can see I cranked it through there, and it's like -1 point something. In other words, the function is decreasing in this interval. And I did the same sort of thing over here at x equals 1/2, and I found that the function was increasing. And then in this interval, I found that the function was increasing, and in this interval, I found that the function was decreasing. Again, all I did is I picked just any number in that range, in that interval, and I plugged it into the derivative to at least figure out the sign of the derivative. The sign is negative, so this is decreasing. The sign was positive, so it's increasing. The sign was positive, so it's increasing. The sign was negative, so it was decreasing. All right, so then all we got to do is apply our first derivative law. Here we have a place where the function beforehand was decreasing and then was increasing. This is going to be a local minimum. Over here, that's an example of that rule I. Over here at x equals 1, the function was increasing and then decreased. That makes this point a local maximum by that rule 2. And over here at this a critical point, the function was increasing, but still increasing then. This is neither by rule 3. Alright, so we found a local minimum, a critical point that was a local minimum, a critical point that was a local maximum, and a critical point that was neither. And if we actually make the graph in Desmos, it looks something like this. Wait a minute, nope, wait. It increases through this whole part. Alright, so we have a domain, an interval where it's decreasing, an interval where it's increasing, another interval where it's increasing, and an interval where it's decreasing. We have a local minimum, we have a local maximum, and we have this inflection point here where it's a critical point, but it isn't actually a maximum or a minimum. Alright. Woo! They're just tedious. We can get a whole bunch of things like that to work for us, though. This is really powerful stuff. Another idea about what we can learn about graphs is a word we've probably thrown around since like algebra with you, but that's concavity. It's hard to define what you mean by concavity in words here. It's kind of easier just to sort of see. Concavity is like, that's concave up. See how it's kind of scooped so that it faces up like it would catch rain? So we would describe that as concave up. Or like this graph is concave down, like it would shed water or whatever. Okay? Functions can have intervals that are either or both. I mean, like this function, for example, here is concave down through this interval, but then concave up through this interval. That's all we mean here. And concavity is related to how the derivative is changing. Look at this function here that has concave up. At first the derivative was big and negative, then small and negative, then smaller and negative, then 0, then small and positive, then big and positive. The derivative of the function was increasing. It went from a big negative number to 0 to a big positive number. Hey, what do we mean by increasing here? We mean headed to the right on the number line, as in getting closer to positive infinity. In contrast, like over here where we have concave down, we started with a big positive derivative, big positive, smaller positives, and smaller positives, 0 derivative, small negative, big negative, big negative. This function has its derivative is decreasing. Again, what do we mean by decreasing? We mean getting closer to negative infinity, headed to the left on the number line. That's all we really need to know about the idea of being concave up or concave down, although I did cut and paste some examples of that in your handout as well as a formal definition of what we meant by concavity there. But it's actually pretty straightforward to test for the concavity at any given location in the function. That's called that theorem 4.10 in your book. It's called the test for concavity. And the test for concavity just means find the second derivative of the function at that location, and if the second derivative of that location is positive, then it is concave up. And you take the second derivative, and if it's negative, that region is concave down. That's pretty straightforward. It's just a matter of remembering or having in your notes for an open note test or whatever how the signs of this work. But it's pretty straightforward here. Probably the easiest way to do it is just go ahead and do an example of it here. Let's do example 419 in your book. That's the one I put in your handout. Okay, example 419. We have a function, f of x equals x cubed minus 6x squared minus 9x plus 30. Minus 9x plus 30. And it says, determine the intervals where f is concave up and where f is concave down. List any and all inflection points and use a graphing utility. Alright, so in order to figure out the concavity, we need to use the second derivative, so we got to get to the second derivative first. Here's the first derivative. Oh man, remember when doing derivatives was hard? Now we got the easy part. Alright, second derivative. There you go. Alright. Now remember, regions are going to be concave up if the second derivative is positive. Regions are going to be concave down if the second derivative is negative, and there's going to be an inflection point if they are changing sign. Alright. Well then, let's look for regions that are concave up. That's going to be places where the second derivative is greater than 0. I bet you didn't think you would be doing this thing with inequalities anytime soon after like algebra. But they were just about exactly the same as equal signs. You can play most of the same rules that we normally do. So look, any place where x is greater than 2, the function is going to be concave up. Let's go look for the places where it's concave down. It's going to be concave down any place the second derivative is less than 0. So the second derivative, which means any place where x is less than 2. The function is concave down any place where x is less than 2. And there's an inflection point any place the second derivative is 0. So we have when the second derivative is equal to 0. Oh, sorry. Second derivative is equal to 0. And that's going to happen where x is equal to 2. That's going to be our inflection point. So we're concave up in the positive numbers. We're concave down. When numbers are greater than 2, we're concave down less than 2, and we are at an inflection point at 2. So here at x equals 2, there's some kind of inflection point. To the right of that, it's concave up. To the left of that, it's concave down. That's bad drawing right there. So this is concave down, this is concave up, and this is the inflection point. And we made a graph there in Desmos to make sure it looks just right. Alright. Woo! Now, one more important rule, definitely on the Ivy Tech's list, definitely on EVSC's list, definitely on the state standards, we definitely have to learn, and that is the second derivative test. Now, here's the deal about the second derivative test. In some ways, the second derivative test doesn't tell you anything you couldn't already get from the first derivative test. It's more a matter of the second derivative test is, well, it can often be easier. And the second derivative test is rather specific in that you have to already know where the critical points are. More importantly, you have to already know the places where the derivative is 0. You have to know you have to already have a list of the critical points, and not just any critical points, just the ones where the derivative is equal to 0. But that's not necessarily so difficult. But once you have a list of such points, you just plug it into that theorem 4.11, the second derivative test there, that just basically says, if you've got this critical point right here, if the second derivative at that point is positive, then this is going to be a local minimum. And if the second derivative is negative, this is going to be a local max. And if the second derivative of that place is 0, the test is inconclusive. We don't know actually whether this is a maximum or a minimum or something else. So the second derivative test, it's actually a pretty straightforward thing. I mean, it just takes up a tiny little area on the handout here. I think that the signs here are hard to remember. I think this is a trap. This business of the second derivative test can be done in a fancy three-dimensional way, and this happens all the time in meteorology, called Laplacians. And I have taught that stuff for 20-some years, and I always got the signs on this turned around. So to me, I think the signs are hard to remember. It's important to realize, okay, if the second derivative is positive, it's concave up. So that place is a minimum. If the second derivative is negative, that means it's concave down, so the place up here is a maximum. I know it in my head, but I get this backward half the time I do it. Probably the easiest thing to do to show how to make this work is to do a quick example, and this is the last thing that we have in the handout. Alright, let's do example 420 from the book. It says, use the second derivative test to find the location of extrema of this function. F of x equals x to the fifth power minus 5x cubed. Alright, in order to do this, we're going to have to find the critical points, not just any critical points, just the critical points where where the derivative is 0. So I guess we're going to need to know the derivative. Okay, so we're going to need to find the places where this is equal to 0. It takes a couple steps to show this here. I'm going to first factor out a 5x squared, so that what's left here is x squared minus 3 is equal to 0. And then it's a little bit fancy algebra 2 stuff to remember that this is x minus square root of 3, x plus square root of 3. Alright. What is that called? Difference of two squares? Alright. So we've got this here. Hey, it's a product that multiplies to 0. It's my favorite trick. So either this is equal to 0, which will only happen when x is equal to 0. Either that or that is equal to 0, which will only happen when x is equal to square root of 3. Or this is equal to 0, which will only happen when x equals negative the square root of 3. Alright, so we have found 1, 2, 3 critical points of our function. Not just any critical points, just the only ones where the derivative was equal to 0. Alright, now, what we're going to do is we're going to take each of these critical points and apply the second derivative test to them. I guess that means we're going to need to know the second derivative. We already got the first derivative, so let's go ahead and find the second derivative. Alright. Now, at each of those points, we're going to apply the second derivative test. We're going to plug this in, 0 in for x. Plug this in and figure out is it positive, negative, whatever. And then from that, we'll know whether that's a local maximum or a local minimum. And that's what I did in the last 3 bulleted points in your handout. At f is f, so we did the second derivative of this critical point, and you get some big negative number. And therefore, this is less than 0, and that makes this a local max. And we'll do it to this critical point next. F of 0 is equal to, you plug it into here, 20 times 0 minus 20, 30 times, it's 0, which means the test is inconclusive. And we plug in the third critical point, which is square root of 3, and you get positive 951 point something or other. It's greater than 0, that makes this a local minimum. Alright, I didn't actually make the graph in here of this, but it looks something like this. There's a local maximum at x equals negative square root of 2. Something weird happens, like an inflection point at x equals, what actually does happen there? I think it goes down and then turns again. And then there's a minimum at x equals there. Something like this. I'm pretty sure it looks something like this. Anyway. Alright. We've worked through these rules. It's the longest handout I've made for you guys. I'm posting the assignment for you on Google Classroom, and I'm also posting an exit ticket. All of this stuff is due on whatever day I haven't showed up for. It's not, I think it's a week from today. Well, it's a week from when this gets posted on Google Classroom. Sometime in the second week of April, I think. But use whatever deadline it says on there. Obviously, if you have any confusion about any of these deadlines, or you've missed some deadlines and you don't know what to do, whatever, always feel free to get a hold of me. I'd be glad to help you with anything. Alright, I think that's everything. Sorry to bother you with an annoying joke along the way. I thought it was funny. And I will talk to you guys later. Have a great day.